In nature, anything that flies has symmetry, and in the early days of human flight, mimicking nature made sense, but as we pushed onto ever higher speeds, our stubborn insistence on symmetry might have been a mistake. In the 1950s, a brilliant NASA engineer began to push for a radical new approach, proving theoretically and with prototypes that aircraft didn't have to be symmetrical. The implications of his work are profound. It suggests we should be flying a lot faster and more efficiently than we are today. Since the dawn of flight, aircraft had been getting faster. In 1920, the fastest plane could barely reach 300 kilometers an hour. By the 1940s, they were already flying 3 times as fast, but there seemed to be a limit beyond which they simply couldn't go. Pilots called it the sound barrier. Above a certain speed, aircraft stopped accelerating. Control became increasingly difficult, and stress forces could even cause an aircraft to break apart in midair. But in 1947, a daring test pilot flew an experimental plane beyond the speed of sound, proving that the sound barrier wasn't a barrier at all. It's just that supersonic flight revolved around a different set of dynamic principles. In the decades that followed, engineers mastered the physics of flying supersonic, pushing speeds ever higher. But a new challenge emerged: designing an aircraft that would perform well in both flight regimes. Any aircraft optimized for supersonic flight would by definition fly poorly at subsonic speeds, because the ideal wing at lower speeds was long and straight, but for supersonic flight it was thin or sharply swept, a shape that struggled to generate lift at lower speeds. Engineers struggled to find a solution, eventually coming up with a kind of wing that could transform in mid-air, functioning more like a straight wing at subsonic speeds and sweeping back for supersonic flight. But variable sweep wings created their own set of problems. Pivot mechanisms had to bear immense lift, rotational and bending forces. Shifts in the center of lift had to be compensated for with larger stabilizers or other systems, all of which added weight and complexity, largely undoing performance gains. Variable sweep wings were only successfully applied to a small number of military aircraft, none of which are still produced today. The sound barrier might not have been an actual barrier, but it seemed that flying faster would always involve serious trade-offs. By 1955, Robert Jones had made a name for himself as one of NASA's top aeronautical engineers. His groundbreaking work on the deltoing, once met with skepticism, had led to the greatest aerodynamic transformation since the very invention of the airplane. But his lifelong passion lay in an entirely different kind of design. It was called an oblique wing, a radical concept consisting of a single wing that rotated on a center pivot. Intuitively, it looks all wrong, as if it would simply corkscrew its way through the sky, but through wind tunnel tests and with radio-controlled prototypes, Jones proved that they were surprisingly stable and controllable, because when it comes to generating lift, the air doesn't really care whether a wing is swept forwards or backwards, so it can fly. But why build an aircraft like this? Intuitively, a highly swept arrow shape seems like the correct way to minimize drag, but that's simply not the case. Jones demonstrated that at transonic and supersonic speeds, the same wing, when arranged asymmetrically, had a much lower predicted wave drag, and so there was no rational reason to favor bilateral symmetry when it was actually less efficient. But Jones's oblique wing had another important advantage: it could also perform optimally at lower speeds by transforming itself back into the ideal straight wing, and compared to variable sweep wings, oblique wings would be easier to build with a single pivot mechanism handling just one force. They would be lighter and less complex, and the center of lift would remain virtually unchanged regardless of the wing's position. Secret German documents uncovered after World War II suggest that oblique wings were even studied as far back as 1942, although no prototypes were ever built on the verge of an aeronautical breakthrough. Jones and NASA engineers were about to change aircraft design forever. This is not an ordinary plane. It has a scissor-like design. By the mid-1970s, NASA moved beyond wind tunnel tests to develop a large-scale remotely operated model that could evaluate the oblique wing's real-world performance and handling characteristics. Meanwhile, leading aircraft designers Boeing and Lockheed were also asked to study oblique wings and evaluate their potential for future commercial aircraft. Both concluded that they could lead to faster, more efficient air travel, but it was Boeing's study that really caught NASA's attention, because by 1975 the dream of mass supersonic air travel had all but faded, as Concorde looked set to become a commercial failure, and it had everything to do with the wing engineers had spent more time developing Concorde's advanced delta wing than any other part of the aircraft, but it was still hopelessly inefficient at low speeds, producing so little lift that Concorde needed fuel-thirsty afterburners to take off, and when countries banned supersonic flights over their airspace due to concerns over loud sonic booms, flying slower wasn't really an option. Concorde wasn't designed to cruise at subsonic speeds where its operating economics were terrible, but Boeing concluded that an oblique-wing airliner would have none of these problems because it would be capable of flying efficiently at a range of speeds and cruise at up to Mach 1.2 without even generating a sonic boom that could be heard on the ground, and that would allow for transcontinental flights over populated areas 50% faster than existing airliners. Power requirements for takeoff, landing and holding around busy airports would also be a lot lower, dramatically cutting noise and pollution around airports. NASA was impressed enough to take the next leap forward. In 1976, development began on a scaled-down version of Boeing's design, not a remotely open model, with the world's first human-piloted oblique WI aircraft. NASA's objectives were ambitious, but the 81 was modest in design. Built mostly from fiberglass, reinforced plastic and foam core, two tiny jet engines provided less than 500 lb of thrust for motivation. The cockpit had only the bare essentials: no fly-by-wire or computer assistance. It would be flown entirely by the skilled hands of a test pilot, built on a shoestring budget. Many at NASA were cautious about investing huge resources into a still and proven concept, but the 81 would back up NASA's research with real-world data. In a total of 79 test flights, the 81's wing was gradually pivoted from 0 all the way to 60. Even flown entirely by hand, control was fairly straightforward, and at lower pivot angles any reasonably skilled pilot could manage, but above 45, maneuvering was more challenging, with a phenomenon called cross-coupling becoming an issue. Pitching the 81 up or down caused it to roll left or right, while rolling left or right caused it to pitch up or down. At a full 60, pilots had to continually bank and yaw to the right to keep the aircraft flying straight and level. None of these issues were all that surprising, and data gathered showed that the 81 would have handled significantly better with an improved wing structure and the help of the computerized flight control system. But the 81 maxed out at just 320 kilometers an hour, nowhere near the transonic speeds where oblique wings could begin to show their potential. For that, NASA would have to turn to a renowned Navy fighter jet. By the 1980s, the U.S. Navy had also taken an interest in oblique wings, because an oblique wing fighter could offer superior takeoff performance from a carrier and increased loiter time. Both were prized capabilities for a next-generation fleet defense fighter to replace the F-14 in 1984. The Navy and NASA signed a joint partnership to develop the first supersonic oblique test bed, and the Crusader was an ideal place to start. Its high wing could be modified to accommodate an oblique wing, and NASA had already experimented with the F to develop fly-by-wire technologies. A modest $36 million were allocated to the project. Design work was to finish by 1986, construction by 1990, and the first test flight was planned for May 1991, but after a successful design phase, the aircraft never got off the ground. In 1986, the Navy caught up in deep budget deficits and cost overruns on other experimental programs. Suddenly pulled funding. NASA couldn't carry the program alone, nor could it find a new partner. In 1987, the project was officially cancelled after nearly half a century. Intensive research into OPWI aircraft largely came to an music, and Jones never gave up on the oblique wing. He continued his research into the 1990s, even at the age of 80, eventually shifting his attention to the development of a pure oblique flying wing, a concept that promised to be the pinnacle of aerodynamic efficiency and fly at Mach 1.5 with operating economics approaching that of a modern subsonic transport. Over the years, dozens of studies have demonstrated the potential of the oblique wing, and in NASA's own words, it remains a viable concept for large transports, but real-world advantages at transonic and supersonic speeds have yet to be tested in flight, and the challenges of flying at extreme WI pivots remain. Modern flight control technologies would go a long way to help realize the advantages, but the aviation industry is conservative by nature. Aircraft today look strikingly similar to those designed over half a century, though the reality is it's less risky for the industry to spend billions in out single-digit gains in efficiency with a proven design than it is to start from scratch with a radical concept like the oblique wing. And that's why well-funded research programs like NASA's 81 are invaluable to the advancement of aerospace. Jones passed away in 1999, having made some of the most important discoveries in the history of aerodynamics, and his groundbreaking research has left many convinced that, despite obstacles, it's only a matter of time before oblique wings take to the skies. Aviation is full of big ideas, but some of them are a little bigger than others. In 1969, Lockheed set out to determine just how large an aircraft could get and what it would mean for U.S. air power. Lockheed's 6,000-ton nuclear-powered aircraft carriers are some of the most fascinating and bizarre aircraft ever imagined. If you like this video, please follow our channel and share it with your friends.